We've been talking about what you can see with your naked eye when you look in the sky at night, and we talked about how Ptolemy came up with a model that turned out to not be very accurate, and then Copernicus, Kepler, and Galileo really ushered in the era of thinking about the sun being at the center of the solar system. Over the next couple of days, we're going to talk about so those were all observational models that they came up with, and we're going to talk about the theory behind why that stuff works. So we'll get into talking about Newton and Newton's laws, but before we get to Newton's laws, we need to first understand a little bit of physics. So today's lecture is going to be on kinematics, which is basically the science of how things move. And we'll boil down how we can use math to talk about how things move into what are called equations of motion. So we're going to talk about how we describe motion. There's some vocab words that we'll need, talking about vectors and scalars, and then we'll introduce some equations and show how to use those equations to, for example, calculate where something is going to be at some time in the future, given some initial conditions. Okay, so here are the first two vocab words that we're going to need when we're talking about physics. There are, in math so far, maybe you've learned about numbers and how to add them and subtract them and multiply them. In physics, sometimes a number needs something in addition to just the number. So a vector is something that has a number associated with it, but it also has a direction. So the examples of things that are vectors are position, velocity, and acceleration. So if I say I'm walking 2 miles per hour, that would just be a scalar because I've only told you what speed I'm moving. But if I say I'm moving 2 miles per hour to the right or 2 miles per hour north, now I'm giving you a value and a direction. And it turns out that the math that you do with vectors is slightly different than the math that you do with scalars. For this class, we won't get too much into the weeds, but it's just an important thing to know. And then, so scalars only have a value. So some things like velocity and speed are related, where velocity is the vector version of speed is the scalar version. But then there are some scalars like temperature that are only ever scalars. You don't say, I have 10 degrees Fahrenheit to the right, or 10 degrees Fahrenheit up. You just say the temperature of whatever object you're measuring. The first vector that we're going to talk about is, or the first physics term we're going to talk about is position. Position is a vector, so that's where something is located in space. So I'm currently at the front of the classroom, so if we said that the door was our origin point, then you could say I'm, from your point of view, maybe 3 meters to the left of the door. In some instances, displacement will be the same thing as position. So if the door is the origin point and I said I'm 3 meters to the left of the door, then my displacement from the door is also the 3 meters to the left. We'll see some examples where position and displacement might be different. Distance is a scalar, and it just says how far apart two things are. So my distance to the door would be 3 meters, And I don't include whether I'm to the left or to the right or above or below the door. And so in astronomy, we're going to be talking about the position of things a lot. We've already talked about how the position of the moon affects the phases of the moon. We've talked about distances between the Earth and the moon and the Earth and the sun that the Greeks were able to measure. And so these things are going to be very important going forward. The common unit for distance and displacement is meters. In this class, we'll need to use different kinds of units when we start talking about the distances to stars. We'll need to use things like light years or parsecs, but for right now, we'll just keep things simple and use meters. So here's where whether you're looking at a vector or a scalar can matter. So we have this example. A person is on their morning jog and they run 3 kilometers in the positive x direction and then 4 kilometers in the negative y direction. And the questions are, what is their current position and how far are they from where they started? And then what is their total distance and total displacement? So let's draw a picture to illustrate what the words are saying. Okay, so the person runs 3 kilometers in the positive x direction. So I'll make a coordinate system. They started here at the 0 point. Then they move 3 kilometers in the positive x direction. So they end up here. And then they move 4 kilometers in the negative y direction. So 1, 2, 3, 4. So now they've traveled this distance and then this distance. Their current position is down here. And the 2 coordinates that represent that position would be 3 units to the right, and then negative 4 units, or 4 units below the axis, so negative 4. And then the units on both of those would be kilometers. So the first question, what is the current position? We've just answered that. How far are they from where they started? So this is where they started, this is where they ended up. So we need this, the length of this line. So if I fill in these 2 values, how do we find the length of this line? Yeah, so this is a right triangle, so we can use the Pythagorean theorem. So this side I'll call C, and more generally for a triangle, if this is side C and this is a right triangle, we'll call this A and B. Then A squared plus B squared equals C squared. So this is the Pythagorean theorem. And so for this triangle, I'll call this 3, or A equals 3, and B will equal 4. So I have 3 squared plus 4 squared equals C squared. So 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. And then to solve for C, we take the square root of both sides. Square root of 25 is 5. And then the square root of C squared, the squared and the square root cancel out, and you're just left with C. So the length of this side of the triangle is 5 kilometers. And so how far are they from where they started? They are 5 kilometers from the starting point. The next questions are, what is their total distance and total displacement? Okay, so distance, we just need to add up the distances that they moved. So they moved 3 kilometers to the right, and then 4 kilometers down. So the total distance is just 3 plus 4, which would equal 7 kilometers. Displacement is a little bit different though. So distance, this was a scalar, but now displacement is a vector. So this is where knowing what a vector and a scalar is will change the value of what you're looking at. So the total displacement is just the distance from, or not distance, but the value from where you started to where you ended up. So their displacement is there's 2 different ways you can display it. In vector form, it would be the 3, -4. The other way you can display it is with a scalar plus an angle. So we already have the scalar, which is 5 kilometers. And then if we want to find an angle, we would use this angle theta, and we would do some trig to figure out that angle. That's a little bit harder math than we're going to need for this astronomy class, but just to show you what that angle would be. We have all 3 sides of the triangle, so we can use whichever sides we want. I'm just going to use tangent because we were given the 3 and the 4 to start with. And so the angle theta would be the inverse tangent of opposite over adjacent, so 4/3. So that's where the difference between a scalar, which was total distance, and a vector, which was total displacement, can change the answer that you're looking for. So the second part of the problem starts after the first part. So the runner has already run 3 kilometers to the right and 4 kilometers down. From that point, the runner now runs 3 kilometers in the negative x direction. So 1, 2, 3 to get back to this axis. And then they run 4 kilometers in the positive y direction, so they end up back where they started. So now they've done this 3 kilometer leg and then this 4 kilometer leg. And so again, the questions are, what is the total distance that the current position, and how far are they from where they started? And then what is the total distance and total displacement? So this point where they started was 0, 0. Then they went 3 kilometers to the right, 4 kilometers down, 3 kilometers to the left, and 4 kilometers back up. So their current position is back where they started. So current position would be this 0, 0. Because using those coordinates, you can figure out where they are in space. How far are they from where they started? Well, they started at 0, 0, and they ended up at 0, 0. So they're 0 kilometers from where they started. To get the total distance that the runner ran, 3 kilometers plus 4 kilometers plus 3 kilometers plus 4 kilometers. So 3 plus 4 plus 3 plus 4. So 7 plus 7 gives you 14 kilometers. Total displacement is how far you are from where you started. So they're at the same place that they started, so their total displacement would just be 0 kilometers. Or you could say 0, 0 to show that they moved 0 in the x direction and 0 in the y direction. So in astronomy, for the most part, we're only going to focus on distances. So we just need to worry about how far apart two things are, and we can just add or subtract the numbers easily. So that was position and distance. Now, velocity is how fast something is moving and in what direction. So position is where you are in space, and velocity is how fast you're moving through space. And that means that there's a relationship between position, or velocity, and position. The scalar version of velocity is speed, and there you just give how fast something is moving. So again, if I'm moving 2 miles per hour, that's a speed. If I'm moving 2 miles per hour to the left or to the right, that's a velocity. And the units for velocity are meters per second. The next nuance that we'll discuss is the average of some variable versus the instantaneous value of that variable. So the average speed of something, you just take the initial speed and the final speed and figure out the average of those two things. The instantaneous speed will be what speed the object is traveling at a very specific time. So you could imagine going from, if you're driving in your car, you go, let's say you get on the interstate to go on a road trip, your average speed might be 60 miles per hour, but before you get on the interstate, you had to stop at a red light, there your instantaneous speed would be 0. So you can have different instantaneous speeds that all come together to make some average speed. And the last way that we'll talk about how things move through space is acceleration. Acceleration is the rate at which something's velocity changes with respect to time. And acceleration we'll see is very important when we talk about Newton's laws next class. The units for acceleration are meters per second squared. So you take velocity, which is meters per second, and divide it by time again, and then you get a second squared in the denominator. And there isn't a special name for the scalar version of acceleration. because acceleration is changing velocity, there are 3 different ways that you can change your velocity. You can increase your velocity, which is the top picture. You can decrease your velocity, which is the bottom picture. Or you can change the direction of your velocity. So in the middle picture, the car is always going the same 60 kilometers per hour, but because their car is pointing in different directions, they're changing their velocity. So in the middle picture, they're not changing their speed, but they are changing their velocity. In the top and bottom picture, they're changing both their speed and their velocity. So again, paying attention to what's a scalar and what's a vector is important. Okay, so here are those relationships between position, velocity, and acceleration. This triangle is basically just a shorthand. So physicists and mathematicians are very lazy. So instead of writing the final position minus the initial position every time they need to write this, they just make a shorthand, or anytime you see this triangle in front of a variable, they mean the change in. And this is it looks like a triangle, but it's actually the capital Greek letter delta. So the way you would read this is delta x divided by delta t, and that means the change in position divided by the change in time. And then acceleration has a very similar looking version of this equation where you replace the position with the velocity. So this is delta v over delta t, which means change in velocity over change in time. So these are the relationships between position, velocity, and acceleration. Starting from these equations, you can get a full set of equations that we call the kinematic equations. And really what these equations allow you to do is predict the future. So given some initial velocity and an acceleration, I can tell you what the final velocity of that object will be at some time in the future. Or, given an initial velocity and acceleration, I can tell you what position that object will be at any point in the future. So when we're talking about how to test our astronomical models, I said the model will tell you where the planet will be at some time in the future, and these are the kinds of equations that you would need to make those predictions. So I need to say, where is Mars going to be 6 months from now? I can use some initial conditions to figure out what position Mars will be in the sky. So that's the power and the value of these equations. The first 3 equations are, the first 2 equations are unique equations. The third and the fourth equations are the same thing, just written a little bit differently. So I tend to like writing the delta x version of the equation, but you can also expand the delta x out to be x final minus x initial, and then you move the initial position to the other side. So just different these 2 are just different versions of the same equation, and whatever the question is asking you to calculate, you'll pick a different version just to make it easier for yourself. So we'll do some examples to show how you can use these equations to solve some word problems. And there is a strategy that I would recommend using when you're trying to solve these equations. So if you take those equations and extract all of the variables from those equations, you get this list of 6 variables. So you have the initial position, the final position, the initial velocity, the final velocity, the acceleration, and the amount of time whatever is happening. So they might give you a time, or you might be asked to find the time. Usually in physics problems, they won't tell you that you start at a position of 0, but you can just assume that you can define your initial position to be 0, usually wherever you want. The acceleration, if you're on the Earth, they might not give you a specific number, but you will just assume that the acceleration is always due to gravity. And we'll talk about that at the end of today's lecture. Another vocab word that they like to use is when something is at rest. That means it's not moving, and if it's not moving, then it doesn't have any velocity. So you'll have a word problem, and the first thing that you do is kind of pull out information from the word problem to fill in this little table of variables. Then you'll pick the kinematic equation that has all of the variables you need except for the one that you're trying to solve for. So we'll do some examples to show how we work through these kinds of problems. Okay, so here's the first example. A car is traveling 20 meters per second when a tree falls in front of it on the road. The car manages to come to a complete stop in 2.5 seconds before it hits the tree. So the two questions we're asking is how far did the car travel, and what acceleration did the car and its passengers experience as it was doing this, going from 20 meters per second to a complete stop. So we need our list of variables. The car is traveling 20 meters per second, so that's its initial velocity. The car manages to come to a complete stop in 2.5 seconds, so the time they give us is 2.5 seconds. And those are really the only two numbers it looks like they give us in the problem. But there's a lot of variables hidden in the way that the problem has been written. So first, we can just set the initial position of the car to be 0. That's usually a safe thing to do. If something comes to a stop, what is its velocity? 0. So they told us the final velocity, they just didn't use a number, they used words. And now the two variables that we don't know are final position and acceleration. And those are the two values that the question is asking for. So we have our list of kinematic equations. And these would be given to you on a test. Okay, so now we go through our list of variables and we try to pick the equation that has only one unknown, basically. Let's find the acceleration first. So we'll skip the first one and come back to it in a second. So what acceleration did the car and its passengers experience? So we're looking for an equation that has the acceleration variable in it. So all three of them have acceleration. We're given the final velocity and the initial velocity and the time. So the first equation has all of those variables. So we could use that one to find acceleration. The second equation, we would need the final position, and we don't have that, so we can't use the second equation. The third equation also has the final position that we don't know, so we can't use that. So we can't use the second and the third equations, but we can use the first equation. So plug in your numbers. The final velocity 0, initial velocity 20, acceleration is the variable we're solving for, and the time was 2.5 seconds. So now you have this equation, 0 equals 20 plus 2.5a. To solve this for the variable a, we need to get it to be on its own side of the equation. So we'll subtract 20 from both sides. So we get negative 20 equals 2.5a. And then we need to divide 20 by 2.5. So 2.5 times 2 would be 5. So this would be 8, negative 8 meters per second squared for the acceleration. And that minus sign is telling us something. It's telling us that this is in the opposite direction as the initial velocity. So the initial velocity was positive and the acceleration was negative. And that makes sense, right? In order for the car to slow down, the acceleration has to be in the opposite direction as the velocity. If it was in the same direction, you would start going faster and you would smash into the tree branch, and that would not be good. Okay. So that's how we find the acceleration. Then we want to find how far the car traveled as it was trying to make this stop. So we fill in our table the acceleration, negative 8 meters per second squared. And we do the same process. So now we want to find x final. We look at all of our equations. The top one doesn't have x final, so we aren't going to use that one. The second equation does, and the third equation does. So you could use either of these equations to solve for x final. I'm going to pick this one because x final is already by itself. So final position equals initial position, which we just set to be 0, plus the initial velocity, which is 20, times the time, which is 2.5, plus 1/2 times the acceleration, which is negative 8, and then times the time, which is 2.5 squared. So you can plug all those things into your calculator, and you'll get the distance that the car traveled before it came to a stop. And that should be on the next slide. Yep. So if the car was going 20 meters per second and it came to a stop in 2.5 seconds, then the acceleration would be 8 meters per second in the opposite direction it was traveling, and the car would stop 25 meters after you started applying the brakes. So this is just an example of how you can use those kinematics equations to solve these kinds of problems. Okay. So one of the things that I talked about was that when you're on the Earth, you can always just assume that if you're moving in the y direction, you have an acceleration that's due to gravity. That acceleration due to gravity near the surface of the Earth is about 10 meters per second squared. So that means that your speed will increase 10 meters per second each second that you're falling. So in this picture, you have someone dropping a ball off of a roof. After 1 second, the ball is traveling 10 meters per second. After 2 seconds, it's traveling 20 meters per second. 3 seconds, it would be 30 meters per second, and so on. So this is some of the tests that Galileo was doing, and one of the insights that Newton had and why his theories were remarkable for their time was he realized that this thing called gravity that affects things falling towards the Earth has to be the same thing that keeps planets orbiting around the sun. And so we'll come back to this idea of gravity later on in the class. Yeah, so Galileo showed that the acceleration g was the same for all objects. So if I tossed a pebble off of the roof versus a bowling ball, they would all have the same acceleration, even if one was bigger than the other one. So here's a question for you. Assuming no air resistance, a bowling ball will fall faster than a feather if released at the same time. Is that true or false? Yeah, so that's going to be false. So the reason the feather falls faster, or you think it would fall faster, is actually because of air resistance. So even though the bowling ball is much heavier than the feather, if you can get rid of the air resistance, they actually fall at the same rate. And so here's a demonstration of that. So this is in a large vacuum chamber, so they've sucked all the air out of this chamber. They drop some feathers and a bowling ball at the same time, and you can see they both reach the ground at the same time. I'll show that again. Gravity affects things the same way, whether they have a lot of mass like a bowling ball or a little bit of mass like the feathers. So we can use those kinematic equations for things moving in the y direction as well. So let's do this example quickly. We have a ball dropped from rest from the top of a 60-meter tall building. We want to know how long it takes for the ball to reach the ground, and then we want to know what the final velocity of the ball is going to be. We have this table that we need to fill in, so let's look through our word problem and fill it in. So the first thing, now we have something moving in the y direction, so we can always assume that the gravity or the acceleration is due to gravity. There's this keyword rest, so if something starts from rest, they're telling you the initial velocity is 0. The second problem asks for the final velocity, so that's one of the unknowns that we're trying to solve for. The time that it takes to fall is also something that we want to find. And so we're left with our initial and final positions. You can define your initial position however you want. Just for things to make a little bit more sense in your head, I'm going to say that we're going to define the ground to be a height of 0. So your final position will be 0 because you're landing on the ground. And that means your initial position will be 60 meters because that's how tall the building is. So this is our list of variables. If we want to find the time, if we look at the first equation and the second equation, those are the only two that have time, or the third equation. The second equation has no time variable in it, so that's not going to be very helpful. The first equation has the final velocity in it, but we don't know that yet. So we're going to pick the third equation to try to solve this problem. So we're picking this equation. the final position is 0, initial position 60, the initial velocity was 0, so it doesn't really matter what the time is. And then 1/2 the acceleration, negative 9.8, and then t squared. So anytime you multiply by 0, you just get 0. So this whole term just goes to 0. So to simplify this a little bit, we have 60, and then 1/2 times negative 9.8 would be negative 4.9 t squared. We want the t by itself, so let's move that to the other side of the equation. So now it's positive. Then we want to divide the 4.9 to the other side. And then to get rid of the square, we just take the square root of both sides. So we're going to take the square root of 60 divided by 4.9. And so you can plug that into your calculator. I'll have the answers on the next slide. So that will be our time. And then to find the final velocity of the ball, I'll just pick this first equation. The final velocity is what we're solving for. Initial velocity was 0. The acceleration is negative 9.8. And the time is the square root of 60 divided by 4.9. And you can plug that into your calculator and you'll get what the final velocity is. So the square root of 60 divided by 4.9 is 3.5 seconds. And then if you take negative 9.8 times 3.5, you'll get negative 34.3 meters per second. So you can say 34.3 in the negative y direction, or you could put a negative sign on your velocity.